Well, good afternoon and welcome to Unit 13, Fundamentals of Thermodynamics and Heat Engines. And we're going to look at Assignment 2 today. So this session is all about preparing you to meet the requirements of Assignment 2. So the assessment criteria for Assignment 2, got one at the top, sorry about that. Explain systems parameters using the no-flow energy equation. So that's really going to address task 1. And we're going to look at apply the steady flow energy equation to plants and equipment. We're going to look at one example in that case, and that is fundamentally task 2. But we'll talk about that. They're all sort of intermingled, these tasks, against the learning assessment criteria. And then we'll derive the steady flow energy equation from first principles, and that's task 3 of the assignment, so that's fairly clear. And then the last assignment set criteria is to produce specific steady flow energy equations based on stated assumptions in the plant and equipment. Again, that's covered in all the tasks from 2, 3, and 4. So that's what we're going to look at in terms of the assessment criteria. So what we're going to do, we're going to review, first of all, the no-flow or the non-flow energy equation. That's in task 1. And then we'll look at the non-flow energy equation examples. Again, that's pertaining to task 1. And then we'll look at development of the steady flow energy equation. And we'll do some examples of application of that equation to a particular piece of plant. And then what we're going to do, we're going to finish off with a review of tasks 2 and 4. Now, tasks 2 and 4 are linked, so that's why I put them together. So we'll look at task 2 and 4. I'm not going to go through the solutions, but there is a solution, a very similar sort of example in the notes. So, but we'll look at the approach to that question in task 2 and 4. Right, so task 1, let's just go through the questions so that everybody's clear what the question is. So we're going to calculate work if the heat transferred out of the system is 200 kilojoules and the internal energy has decreased by 700 kilojoules. And also going to state whether that work is done on the fluid or by the fluid. So that's a typical question. So we'll do a few examples along that line. Right, first of all, let's look at the non-flow energy equation, sometimes called the no-flow energy equation. So in a non-flow process, one that hasn't undergone a cycle, that's important. That if it undergoes a cycle, then the net condition of the system is the same at the end as it was at the beginning. So we're looking at an incomplete cycle. So that means we've added heat and work has been transferred in or out of the system, and that has an effect on changing the energy within the system itself. So we'll do some examples on that in a minute. So last week we looked at the no-flow energy equation. We looked at defining the system boundary. We looked at transfers of energy in the form of heat and work. Please. Right, carry on. So by conservation of energy, we have Q minus W, Q being the work heat transferred, W being the work transferred in and out of the system. And because we have not gone through a cycle, that's going to result in a change in the energy within that system. And we call that delta E. However, delta E is made up of a few parts. I'll just use a pen. Pointer. So delta E has internal energy due to its temperature. It also contains potential energy and also kinetic energy due to the movement of the fluid within that system. However, for a closed system, potential energy and the kinetic energy are almost a constant. So we can ignore those two terms of potential energy and kinetic energy. Because there's no movement, there's no change in height, there's no velocity associated with that fluid, a mean velocity associated with that fluid. So our no-flow equation or non-flow energy equation changes to Q minus W is equal to delta U. And Q is the heat transfer in and out of the system, W is the work transfer in and out of the system, and delta U is a change in internal energy within our system boundary. So let's do a few examples based on using that equation. So question 1, or example 1, the energy of a system increases by 25 kilojoules while the system is receiving 20 kilojoules of work. How much heat is transferred and in what direction? So that's very similar to the assignment in task 1, isn't it? Before you start, the first thing to do is always to draw a system boundary, an imaginary system boundary. So we'll create a system boundary and show the direction of the energy transfer. So we've got work out and we've got heat in and out. Now the sign convention is work out is always positive, work in is negative, and heat transfer, the sign convention is heat out negative and heat in is positive. So it's always useful just to do a little sketch of that on the side before you start these questions. Otherwise, you're going to get into trouble with the sign convention. Now, the way to remember this, as I said last week, is that work out is positive. Think of this as being a reciprocating engine. So the work out is positive. That's useful to us. So it's good. So it's positive to us in general. So that's the way to remember that. Work out is positive. So the heat out is the opposite, is negative. So it's a way of remembering the sign convention. Okay, so we'll start off, we'll write Q minus W is equal to delta U. Starts with our non-flow energy equation. Right, so what we've got, the energy of the system increases by 25 kilojoules. So that means delta U is equal to plus 25 kilojoules. What else have we got? While the system is receiving 20 kilojoules of work. So it's work in, so it's negative. So delta U should be there. So the work is equal to minus 20 kilojoules. So that's the work, receiving work. So receiving work is negative. So we now put our numbers into our equation. So Q minus W, W is minus 20. That's equal to delta U, which is 25. So if you rearrange that, you get Q is equal to 25. I've got a minus next to a minus, that becomes a plus. We take it to the other side, it has to become a negative. So it's minus 20. So it's equal to plus 5 kilojoules. Because it's plus, the heat Q is plus, that means it's into the system. So that's in to the system. Okay, so that will do another question. So let's move on to the next question. Part B, very similar. So the energy of a system decreases by 50 kilojoules, whilst the system is receiving 60 kilojoules of work. How much heat is transferred? Again, draw your symbol, your system boundary, indicate the work transfer, the heat transfer, and put the sign convention on. Remember, work out is positive, so everything else is opposite to that. So it reminds you of the sign convention. And we'll start off with our no-flowing energy equation. Q minus W is equal to delta U. So what have we got? Well, the system decreases, the energy of the system decreases by 50 kilojoules. So that means delta U is equal to minus 50 units, whilst it's receiving 60 kilojoules of work. So that means the work is going in. So work in is negative. So it's going to be minus 60 kilojoules. So all we have to do now is put our numbers into our equation. So we have Q minus W, and W is minus 60. And that's equal to delta U, which is minus 50. So we've got a minus and a minus, so it's a plus. Take it to the other side, it becomes a minus again. So Q is equal to minus 50 minus 60, and that's equal to minus 110 kilojoules. So Q is negative, so that means it's out of the system. Now the direction is out of the system. Right, so we'll do one more example, and I think by then you will have got the hang of this. So example C, very similar type of approach again. So during an expansion process, the work done and the heat received by a system are respectively 20 kilojoules and 50,000 joules. Calculate the change in energy of the system. So we'll start off, write our no flow energy equation. So what have we got? The work done and the heat rejected by the system are, so the work done by the system are 20 kilojoules. So the work done by the system is plus 20. So work done is equal to plus 20 kilojoules. The heat received is 50,000 joules. So Q is equal to, and it's received by the system, so that means it's positive, so it's plus. I'm changing to kilojoules, so they're all in the same order. So we have 50 kilojoules there. So now all we have to do is calculate delta U. So Q minus W is delta U. Q we have as 50 minus, and it's usual to put brackets around your work components. It's plus 20. That's still going to be minus, isn't it? And that's equal to delta U. So we can write that delta U is equal to 50 minus 20, which is equal to 30 kilojoules. Yeah, and it's a positive value, so it's an increase. In internal energy. So I think that'll really set you up for doing task one. You shouldn't have any problems with task one by following those examples. So task three, now you notice I've jumped from task two to task three, and there's a reason for that. We'll come back to task two at the end. So task three is derive the steady flow energy equation from first principles. Oh, there's no way of me not showing you how to do that. Otherwise I wouldn't be able to do anything. And it's important that you understand the derivation of the steady flow energy equation. So what we have, we're going to apply the first law of thermodynamics to an open system that's subjected to a steady flow. And we call this the steady flow energy equation. So think of a system there. We've got a system shown there. It's got an inlet and an outlet, and part of the system, there'll be heat transfer, Q, and there'll be work transfer, W. Now, I know I've shown one out and one in. It's not that important at this stage. The thing to note is that the fluid entering the system has velocity C. It has internal energy, which you're going to call U. It has a height from a datum Z1. It also has a pressure and it has a volume. So that's the fluid flowing in. We've also got to look at the fluid flowing out. The fluid flowing out will have velocity, also has internal energy, has a height due to its position, it has pressure, and it has a volume. So they all form parts of the energy flowing in and the energy flowing out. So what we've got to look at is that the system above is exchanging heat and energy with the surroundings, isn't it? But it's also going to be subject to flow of a working fluid which passes through that system. The fluid entering and leaving the system, and it possesses energy in the form of kinetic energy due to its velocity. It possesses potential energy due to its position relative to the datum. It also possesses internal energy due to its temperature, and also it has energy due to its pressure and volume. Now, you may not have come across this before, but it's referred to sometimes as pressure energy, and it's the energy necessary to get the fluid to flow into the system and to flow back out of the system. So we'll look at the pressure energy first. So we'll do each term as we come to it. So we'll start off with the pressure energy. So first of all, if we look at our system on the inlet, so we've got fluid flowing in that direction. It has a pressure P and it has a surface area at the inlet of A. So the force pushing that fluid in is equal to the pressure times the cross-sectional area. So the incremental force on the fluid element is simply the pressure times the cross-sectional area of that part of fluid particle. And we also know that the work done by the fluid is a force times the distance moved. So if that fluid moves from where my pointer is there, where my pointer is, from there to there, then work has been done on that fluid, and that work done is the force times the distance moved. Now the force is pressure times area, and the distance is delta x. So the work done is P, pressure times area times our delta x. Also, our area, A, times delta x is actually the volume of that particle of fluid. So it's equal to P times V. So that's what we call the pressure energy, or sometimes it's referred to as the flow work. So it's the energy necessary to get the fluid in and out of the system. The other terms, you're probably familiar with these, is that the fluid has kinetic energy due to its velocity, and that's given by half times the mass times its velocity squared. So we're familiar with that. You've done that before. And you're also, the fluid has potential energy due to its height, and potential energy is the mass times G times its elevation above the datum Z. So that's the two, kinetic energy and potential energy. So now we're going to look at the entire system and apply the first law of thermodynamics. So the thing to remember is that Q minus W is equal to two components this time. It's the net energy transported by the fluid. So that's what's transported by the fluid in, and less the energy transferred by the fluid out. So that's the net energy transported by the fluid, plus the change in total energy stored within the system. So it could be a change within the system, inside that system where the energy increases. So we'll just go back to the previous slide. So what we have the energy flowing in, energy flowing out. So the net difference in the flow of energy is the difference between the inlet and the outlet. But also you could have a buildup of energy internal to the system. So we've got to take care of that in some sort of way. So putting that in an equation format, we have Q minus W is equal to the energy in the fluid leaving minus the energy in the fluid entering, plus the change of energy internal to the system. Like, one thing to note, and this is very important, if we're looking at steady flow conditions, then the total energy of the system is going to remain constant. So our term, delta E term, becomes zero because there's no change to the internal energy within that system because we've got steady flow conditions. Yeah, so the mass flow in is equal to the mass flow out. So our equation reduces to Q minus W is equal to the energy contained in the fluid leaving minus the energy contained in the fluid entry. But we already know that the fluid entering and leaving contains quite a number of different types of energy components. So we'll note those down. So Q minus W. So the energy leaving is the pressure energy, P2V2, plus its internal energy, U2 times its mass, plus the kinetic energy, plus the potential energy. And entering, we had, again, the pressure energy, P1V1, and we have the internal energy in that contained in that fluid entering. It has kinetic energy and it has potential energy. So all we're going to do, we're going to divide throughout by mass. So we're going to divide through by the mass components. So we're going to cross these mass components off. Yeah. So we end up with Q. Now you'll notice we've changed Q now to a lowercase. So it's Q minus W in lowercase. That means it's a specific heat transfer. So this Q would be heat transfer per kilogram of fluid, and this would be the energy transfer through work per kilogram of the fluid, as we've divided throughout by mass. That leaves us with the pressure work, plus the internal energy, plus the kinetic energy, plus the potential energy. However, there's probably a property that we haven't come across before, the property that we refer to as enthalpy. And enthalpy is made up of the internal energy of the fluid due to its temperature and its pressure and volume ratio. So PV plus U is equal to H, the enthalpy term. So we can replace these two terms with the enthalpy H. So our steady flow energy equation becomes Q minus W is H2 plus half C2 squared plus GZ, and similarly on the outcome, on the inlet. So that's referred to as the specific steady flow energy equation. Don't forget, these now are specific quantities. So Q and W are usually in joules per kilogram. Just write that a bit better, which is specific heat transfer. So you may want to use that when you come to assignment 2 and 4. Right, let's move on. Let's look at an example of application of the steady flow equation to a turbine. So it could be a gas turbine or a steam turbine, doesn't really matter, the same principles apply. These devices are usually, the heat transfer is usually quite small, they're usually quite well lagged if you have a transfer. So this could be hot gases from a combustion chamber. It's expanded across the turbine to the exhaust. And in so doing, it gives up its energy and drives an output shaft. So again, it could be a steam turbine or a gas turbine, same principles. So we'll start off with our steady flow energy equation, where Q minus W is H2 plus half C2 squared minus GZ2, and that's less the energy in the fluid entering, which is H1 plus half C1 squared plus GZ1. Now, the thing to note about it is that if you look at the actual value of the terms, enthalpy is usually measured in 1,000 plus kilojoules of energy. But if you look at the velocities, which tend to be quite small, then they're orders of magnitude difference. So the velocity might be, say it was 3 meters per second, 3 squared is 9, divided by 2. So the total energy and the kinetic energy is, well, you know, it's 3 meters a second. We're talking about 4.5 joules of energy, whereas the enthalpy is usually in the order of 1,000 kilojoules. So there's a massive order of magnitude difference. So we are legitimately, it doesn't influence the answer. So we can actually cross the kinetic energy terms out because they don't play any significant part in the actual calculation. And the same with the value of Z. So if it was a difference in height between the inlets and outlets, it's usually very small. And again, the energy in difference is minute. So again, we can cross them out and they become 0. And usually a turbine is well insulated, so Q will approach 0. So we can actually cross that out as well and become 0. So our steady flow energy equation reduces to the work done. Specific work is simply the change in enthalpy. Now, enthalpy, you may not have come across that term before, but the enthalpy is simply the specific heat at constant pressure times the temperature. Enthalpy H is equal to specific heat at constant pressure times the temperature. So H1 minus H2 is simply specific heat at constant pressure for that fluid. For air, it's just over 1 kilojoule per kilogram K, and that will be times T1 minus T2. Yeah, so that gives you the enthalpy for air. So for air, Cp is equal to 1.005 actually, and that's kilojoules kilogram K. So that should give you some sort of idea towards assessment task 2 and 4. Right, we're going to come to task 2 now. And I've included task 4 in there. And there's a reason for doing it because they are linked together. So let's first of all, so a power plant's working fluid can be modeled for perfect air, which flows around a system at 90 kilograms a second. So that's the mass flow. The working fluid enters the compressor at 330 K and 0.4 megapascals, and it leaves at 4.8 megapascals. Where it enters the boiler, it leaves the boiler at 450 K, where it enters a turbine, and then it leaves the turbine back at the original pressure of 0.4 megapascals. Now, this is the important part of this question now. Assuming that the compressor and turbine are isentropic, and gamma is equal to 1.4. Now, it's very important is that you understand that it's an isentropic process, which means it's adiabatic. So remember last week, we had the index of compression N in some of our equations. So for an isentropic situation, N is equal to gamma. Yeah, so P V to the gamma is equal to a constant. Now, this will make a bit more sense, hopefully, a bit later. So what you've got to do is you've got to determine the exit temperature from the compressor, the exit temperature from the turbine, and the thermal efficiency of the compressor. Now, there's an example of this in the notes, so be careful that I don't say and do too much. Otherwise, I'll be answering the question for you. We'll come back to task 4 in a minute. So when answering this sort of question, what you should do, the first thing you should do is draw the system out. So we've got a compressor, a boiler, a turbine, and the flow. So we have air flowing into the compressor. We've got the pressure. We've got the temperature at 0.1. We also have the pressure at 0.2. We don't have the temperature. That's something we need to calculate. We're given the temperature at 0.3. And we know the pressure at 0.3 because it's equal to the pressure at 0.2. So let's make a note of that. So P2, so write down what you know. So P2 is equal to, I need to go back and have a look. I can't remember. So P2 is 4.8 megapascals. So it's 4.8 megapascals. P2, we don't know, so put that as a question mark. At condition 3, we have P3 is equal to P2. There's no change in pressure. And we have T3 is equal to a question, is given in the question, and T3 is 850 kilopascal Kelvin. We also know P1. P1 is 0.5 kilopascals. And we have T1. And T1, just go back, always keep going back, is 330. Oh, anybody spotted my deliberate mistake there? So I need to rub that off, don't I? So let's erase that bit. So I need to erase the pressure there. So the pressure was 0.4 kilopascals. And we also know that P4 is equal to 0.4 megapascals. So another, let me just correct that. Oh. Just change that to megapascals. It's always useful to check this before you do too many calculations. So take all the information from the question, draw the system out, take all the information from the question, put them on the drawing so that you know where you're going, what numbers you're going to pick up, that you don't pick up any wrong data. Now, because we're told that it's an idealized isentropic process and that it's adiabatic, that means P2 over P1 is equal to T2 over T1 to the power gamma over gamma minus 1. That's in the handbook. So from that, you can calculate T2. Likewise, when you look at the turbine side, we can use this same equation, except you have P3 and P4 in there. And you can use the same equation to work out the temperature at T4. So T4, we don't know that temperature, T4. I think that's what you calculated. Now, we don't know what happens in between T4 and back to T1. So there may be a change in temperature. There's some sort of heat exchangers in there. We don't know, but don't be sort of concerned about that at the moment. So that's going to answer part A and part B. Part C, I think you need to have a look through in the notes of the example that's in the notes and work out the thermal efficiency of the compressor. Now then, the next part in task 4 relates back to task 2. So it says, determine the specific work of the system. Now, I've got to be careful here what we mean by the specific work. The specific work is the work output per, so the specific work is simply the work output in joules per kilogram of fluid. Now, we've got to be careful because the turbine will have us do a certain amount of work, but some of that work is used to drive the compressor. So the net work out is simply the turbine work less the compressor work. So what we've got left is the difference to do some useful work in driving something like a generator. So the net work is simply the turbine work minus the compressor work. Then you're asked to determine the power output of the system. Now the power output is simply the specific work times the mass flow. So if we look at the units of that, we have specific work is in joules per kilogram. I'm going to multiply that by mass flow, which is kilograms per second. Of course, the kilograms cancel out, and that gives us joules per second, which is watts. Yeah, normally it'd be in kilowatts, in kilojoules per kilogram. So it'd be in kilowatts, kilojoules per second is 1 kilojoule. So just one last part to that question was the backwork ratio. And what the backwork ratio is quite straightforward. And there's actually a formula for doing that. The backwork ratio is the ratio of the amount of work produced by the turbine that's used by the compressor. So if the compressor uses half of all the work done by that turbine, then the back ratio would be 0.5. So it's compressor work divided by the total turbine work. So that's how much work is back-fed to drive the compressor. That's why it's called the back ratio. So that's, again, there's an example in the notes that would help you do that. So all I can say, if you've got any queries, any questions, please don't hesitate in getting in touch. I put my details up at the end. So just to sort of reiterate, when you submit your assignment, include the contents page, identify each task by the letter or the number. So task 1, 2, 3, and 4 in this case. Type everything up. However, equations can be handwritten, providing that you scan them as a PDF and insert them into your diagram, into your work, and that they're actually neat and we can read them. Use images, tables, charts to support your answers. No problem with using that off the internet, whatever you want to use them from. But don't forget, you have to reference these images if you get them from somewhere else. And you also have to refer to them in the text. Otherwise, the images have no purpose. So if you put an image in there, in the text, that's supporting text, write something along the line. This is clearly shown in figure 2. So we can relate the text to the image. Otherwise, the image has no purpose. You may as well not bother putting it in. So include accurate citations and referencing. So everything that you've used that's not your own work, you must reference it in the reference list and say in the work, and it's called a citation, where you've actually used that reference. Yeah. So if there are any questions, those are my contact details. So if you want to get in touch about the assignment 2, please feel free, or assignment 1, please feel free to get in touch with me. Send me an email, your contact details and availability, and I will bring you back as soon as I possibly can. Okay, so do we have any questions?